Welcome to Lecture 2 of Embedded Systems. This lecture is primarily about the assembly language syntax and programming for the microcontroller, and I shall begin by introducing the basic logic shift operations. That will be followed by the addressing modes, memory operations, and writing subroutines. And in the end, I shall quickly cover the reason of programming microcontroller in C language, and the formal introduction to the C language will be covered in the next lecture. The lecture agenda items include assembly language syntax with the help of examples of how to program microcontroller to execute the logical operation and the shift operations, and also various means to access the memory that is inside the microcontroller and that is to be used for our programs or user-defined applications. A part of that description will be about different formats to access memory. Those formats are known as the addressing modes. And in the end, we shall cover the basics of stack and the role of stack in the implementation of routines and subroutines. And the lecture will be concluded with the migration to the C language, although the details of that will be covered in our next lecture, that is lecture 3. So we begin with the logic operations that you are already familiar with, such as the AND operation, the OR operation, and we introduce here some new operations such as the BIC operation, that is essentially the AND of A and NOT of B, and OR N, that is the OR operation between A and NOT B. Exclusive OR operation, it is E OR, that stands for exclusive OR. Those are the operations, the logic operations which are supported by the microcontroller, and you know very well how to implement those operations with the help of logic gates. But here we are going to talk about the logic instructions, meaning that what are the instructions that we can give to microcontroller to execute the logical operation. Those are the same as we have just described, the AND, OR, exclusive OR, BIC, and OR NOT. Now in each of these instructions you have some operands. First of all, look at this, the first operand over here that is inside the parentheses. Any operand that is inside the parentheses means it is an optional operand. It is an optional operand. The second operand is represented by a generic name, that is Rn. That is going to be some register. It is going to be a register. And the third operand can be anything representing a register or some constant. So for example, if we want to perform an AND operation between this operand, that is the register Rn, and some other operand, can be register, can be a constant, the AND operation is performed. It's a bitwise AND operation, and the result is going to be stored in the third operand, that is the first operand on the left hand side. In fact, this is RD, the third operand. Now if this operand is missing, if you do not specify this operand, then the destination, the result, is going to be stored in Rn. That is, this can be your destination register, destination. It is your destination register if you do not specify the third operand. That is the first operand from the left-hand side. Now remember, the registers are 32 bits long in the microcontroller, unless you are running in the thumb mode, which will be described in the next lecture or sometime in the future. And finally, what about this S suffix? Yes, this S suffix indicates a special meaning to the instruction, which will be covered in our next lecture, in which we shall describe that if the instruction is AND S, then it is performing an AND operation as already described, but this S is also going to change what we call as the code bit. So S, if specified, represents that we are going to modify the code bits. These are special bits that are used to control the flow of the program. Again, this lecture will not cover the code bits except for only one of them, that is the carry bit. Let us look at how the OR operation can be used to set certain bits of a variable stored in the memory. In this code segment that is written in the assembly language, we are going to read that variable. The variable is GPIO port D direction underscore R. So that is a register that is to set the direction of the port D, as we discussed in our last lecture. So in this case, we wish to make the last two bits of port D, that is the last two pins, or you can say the first two bits, pin 0 and pin 1, as the input ports, where we are going to set these, set the two pins, set the two bits in this variable to equal to 1. And we're going to, and how we are going to do that? Well, we're going to take an OR of this variable. So remember, this is a variable that is stored in the RAM. We're going to take the bitwise OR operation of this variable with hex 03, which is basically this number. This number, hex 03, is this number. Okay, so the first instruction is basically loading the address of this port D variable inside the register R0, and then we are going to read the value of the variable using the second instruction that goes into R1. But the main instruction of this slide is this OR operation. So once we have fetched the value of that variable, whatever the value is, so for example, in this case, the value is written in terms of some generic variables starting from C0, C1, C2, C3, C4. All of these C variables are binary variables, so it can be a 8-bit binary number. So whatever the value is, we are going to first store that value in the register R1 and then take an OR, and then the result goes into the same register R1. So once the result has been updated in the register R1, we are going to store it back to the variable pointed to by register R0. So remember, register R0 contains the address where this GPIO variable is stored. Again, these LDR and STR instruction will be discussed once we have described the logical instructions. So we just have to wait before the complete description of the load and the store instruction is provided. The same goes for the store instruction, the exclusive OR instruction. So the instruction 3 in this case is taking the exclusive OR of the same memory variable with hex 80, which means we are going to take the exclusive OR of the variable. This time the contents of the register are shown by these B bits, starting from B0, B1, B2, all the way to B7, and this is the number that is hex 80. So if you take an exclusive OR, only the only bit number 7 will be toggled because it has been exclusive OR with the value 1. All other bits remain unchanged because the value the values are all zeros. So if you take a 0 exclusive OR with any bit, the bit value remains unchanged. Our next example is the use of the logic operation AND. And in this case, we are going to use this operation to store the data read by a bit that is actually the pin A6 on port A. There's a switch that is attached. So if you focus on this part of the diagram, the positive logic one, there is a pin that is the 6th pin of port A connected to the switch, and the switch can be open and close, and we are assuming that we have configured port A as the or we have configured bit 6 of the port A as the input pin. Then if you're interested in knowing what is the value read by what is the value, what is the input value available over here, is it 0 or is it 1? So remember, if the switch is closed, then we have a 1 over here, logic high, and if the switch is open, then we are going to have this pin connected to the ground with the help of resistance, so that is going to be 0. Okay, so we are going to use the AND operation to first of all mask all other bits, all other pins, or the data available on all other pins of port A. We're going to mask those values to 0. So all other pin values, that is A1, PA1 to 5 and PA7, they are set equals to 0. How to do this? Well, for this step we need to perform an AND operation, right? So this AND operation is applied to register R1, which contains the value of GPIO port A data underscore R. So that value is being read into register R1, and then we take the AND operation. And obviously that value will tell us the value at bit number 6 is going to tell us the switch open or closed status, and once that has been that value has been recorded and we have masked all other values that we are not interested, because this is the this pin is the input pin. That's how it is configured, port A. So once that is done, then we are going to store the value back to another variable that is pressed. So over here we have this variable pressed, which is just the bitwise AND operation of the port data and the 8-bit hex number, 2-digit hex number, or 16-bit number, 8-bit number, and we're going to store it back to the new memory variable. This time it is pressed. So the pressed address is read into register R0, and then the result. Okay, the result. So where is the result? The result is in R1 over here. The result of the AND operation, that is going to go to the location pointed to by register R0. And what is that? That in this case is pressed, this variable. So the thing to note is that in the beginning of the program, R0 was basically pointed to, so I mean let me do it real quick. So in the beginning, remember that R node was pointing to GPIO variable, and by the end the R node was pointing to this new memory variable press. So again, just like GPIO variable, press is also a variable that is stored somewhere in the memory. All right, then we have different types of shift operations, starting from the logical shift right. So in this case, if we apply this logical shift operation on the register, remember register, as I said in the beginning, was 32-bit register. So we're going to apply the shift operation to the 32-bit register. So what it does is that it inserts 0 to the most significant bit or the leftmost bit, and then shift all the bits to their right. Eventually we reach at the least significant bit that is pushed out and goes to a storage, a bit storage that we call, this is the carry. It is one of the code bits that I talked about in the beginning. It's a carry bit. So whatever is shifted out of this register goes into the carry bit. It is one of the code bits. The remaining code bits will be discussed in the next lecture. So that is the logical shift, in which we are going to push bit 0 from the left hand side, from the most significant bit side, and we're going to push out the least significant bit that goes into the carry code bit. What about the arithmetic shift? The arithmetic shift is again going to push all the bits to their neighboring bit location. So all the bits are shifted right as before, and the least significant bit is shifted out going into the carry bit. But we're not going to insert 0, rather we are going to copy or retain the value of previous value of the most significant bit. So if the previous value of the most significant bit was 1, it remains 1. Right. And the use of arithmetic right shift is to maintain the signed nature of the number. We know that in the signed binary arithmetic, the most significant bit matters. So 0 usually means that the number is positive, and the 1 means negative, as we all know. So we want to perform an arithmetic shift operation that preserves the sign of the number. Then comes the logical shift left. Okay, logical shift left. In this case, we're going to shift all the bits to the left, and then the most significant bit is shifted out and goes into the carry bit. That's logical shift. So one of the differences to note over here is that the arithmetic shift copies the, or it actually copies the bit, like in case of arithmetic shift right, the most significant bit was retained or copied back to its original location. In logical shift, the bits are not copied. So in this case, the 0 has been, in case of logical shift left, the 0 has been entered from the right hand side, and this is how it works, and all the bits are shifted left. The rotate shift right is the next instruction. It actually performs a variant of the shift operation in which the bit which is shifted out, because this is a right shift, so we are going to go counterclockwise, I should say. So all the bits are shifted right. The bit that is shifted out, the least significant bit that previously went to the carry bit, is copied or goes back to the most significant bit. So that's why this is a rotation operation, that the bit that is shifted out rotates back over here. That's rotate shift right. And then finally we have rotate right extended, RRX, in which we utilize the carry bit as to extend the size of the register. So again, all the bits are shifted right. The bit that is shifted out from the least significant position goes into the carry bit, and then the carry bit goes back and it enters the register from the left hand side. So this is how the RRX works. As far as the syntax of the logical shift left instruction is concerned, we're going to focus on the third instruction in the code segment. It says LSL R1, comma R1, comma hash 4. So 4 is the shift amount. That is 4. So we essentially, this says that we're going to shift 4 bits to the left, and it's a logical shift. So we're going to say logical shift 4 bits left. So when you do logical shift left 4 bits, and that if that is done on register R1, so assuming the initial contents of the register R1 was such that the lower 4 bits had some has some information such as bits B0 through B4, and the upper 4 bits were 0. So when you apply logical shift left, all these 4 bits, that is these 4 bits, are shifted up. These are now going to become the upper 4 bits, and when these bits are shifted left, it automatically creates space for the incoming zeros. So eventually we are going to have 4 least significant bits containing 0. That's consequence of this logical shift operation. And these B's, B0 through B3, actually these are H, so H0 through H3 are shifted left. These are now the upper 4 bits in the byte. And then we are going to perform the OR operation with R2. So taking the OR operation, R1, R2 going back into R1. And remember, R2, according to this code segment, that contains the low variable. So the high variable contents were contained in R1. The low variable contents are contained in R2. So by taking the OR of these two, we have combined the contents of two registers such that the upper 4 bits are coming from register R1 over here, and the lower 4 bits are coming from the register R0. Yes, over here. And we have combined the two. We're now going to formally describe the syntax of the assembly language. So 3 things to note. First of them, I think we have already seen 2 of them, the opcode and the operand. So we have seen instruction, load, store quickly, and then we have discussed the logical instructions and the shift instructions, such as LSL, such as OR instructions. So that instruction part describing, telling microcontroller exactly what to do, is contained in the opcode. And the operation, operands, we call them operands. Operands are operands are actually the registers or constants or the memory locations on which the operation needs to be performed. So in this case, they have described the syntax with the help of an opcode, which is move, and the operand. So this instruction really says that move number 100 into register R0. But we have something new as well, that is the label. So if I parse this first instruction, then we can say that there's a label. This instruction move R0, comma hash 100 has a label, and this label will be used in branching. So when an assembly program needs to move back and forth, um, it needs to, so if for instance assembly program is executed and at some point we realize that we need to go back to the same instruction, then the move instruction, then that instruction is identified by the label. Essentially, this label over here, for example, the label over here is init. That is actually an address. It is actually an address of instruction. It is an address of this instruction. Comments are optional, but good programmers would always put some comments so that the reader can learn why the instruction was there and what it was doing. So commenting is an important part of this assembly language program. There is another instruction which is bxlr. Okay, so this instruction is actually performing a task that we call as the return operation. So it is typically used when this core segment is used as some kind of a routine or subroutine. It is so bx means that branch to go back to the location, go back to the address specified by the link register. So LR is the link register, and bx says that go back to the address contained in the link register. Address contained in link in LR, just in LR. LR is also identified by register R14 inside the microprocessor. More details will be described in the stack section. An important consideration in writing a program in the assembly language is the specification of the operand 2. So for example, if you wish to add, so this is an add instruction, add RD, RN, and operand 2. So as an example, so suppose we wish to add Rn is some register, let's say register R0 to some, we wish to add some constant to register Rn and then store the result in register Rd. Okay, so that can be done in a variety of ways. For example, you can actually apply shift. You can actually use operand 2 in a way that first apply the shift operation, like in this case. So for example, we wish to say add R0, add R0, comma R1 LSL 4. So this instruction actually performs a logical shift left on the register R1, and the shift amount is 4, which is same as multiplying R1 by 16, right? So remember, if you perform a logical shift by 4, then it is going to multiply the number with 16, and then it is going to add R1 with R0. So multiply R1 with 16, add it to R0, that goes back into R0. Similarly, you can have another instruction, add R0, R1, R2, ASR, that is arithmetic shift right 4. So apply arithmetic shift to register R2 by 4. That is equivalent to dividing register R2 by 16 and add it to R1 and store the result in R0. So remember, the leftmost register turns out to be the destination register. It is the destination. It is going to be the destination if specified. So this is the destination. That's where the result is going to store. So inside the microprocessor, you can only store the result inside the register. You cannot have a memory location or an address. So that has to be some register over here. This ARM cortex-m4 processor is a RISC processor, reduced instruction set computer, in which, when it comes to accessing the contents which are neither constant nor contained in the register, but those are in the memory, then there are several different ways. There are some rules that we need to follow. For instance, you may be interested in accessing a constant stored in the read-only memory. How can we access that constant? For example, we might be interested in accessing a portion of memory allocated as stack. We may be interested in the variables stored in the memory, in the RAM. Some of those examples came earlier in the lecture. And finally, we might be interested in accessing the I/O ports. Again, we've seen examples of that previously. So let us now delve into the various mechanisms of accessing memory that is to be used for our application, and it is a memory that is inside the microcontroller that we can program for our purposes. One way to access data is to store the data as part of the instruction. That is, data is contained inside the instruction, the data that we wish to process. So we saw an example of a move instruction where we said that move R0, #100. That is, we were trying to move the value 100, that is in decimal, not in hexadecimal. So that goes into R0, and that value 100 is part of the instruction that is stored as part of the instruction. So in this example, if I represent the memory as the slots, a list of the listed slots, and against each slot these are the addresses, and this is the portion of the memory that stores code. That is the EEPROM, electrically erasable programmable read-only memory. That's where the code is stored. So there is an instruction, and because everything inside the microcontroller is stored as a binary number, so this is a 32-bit. This is an example of a 32-bit instruction. So it has 8 hexadecimal digits. So 8 hex digits. So this instruction is stored as at an address that is hexa 00000264. There is a register known as the program counter, PC, also known as the program counter. Is a very important register, and this register contents are shown over here. That is the same as hex 00000264, which actually represents the address of the memory. So this is the same thing. The address, the PC contains an address containing the instruction that it needs to execute. So remember, the program counter points to the memory location containing an instruction. So here, so this is a 32-bit instruction. So this is a 32-bit instruction. What is that in binary number? In fact, in hexadecimal digits, F0, F4F, not 0064. So it'd be better if I just say F04F 0064. It's a 32-bit instruction. It is contained in the memory, and the program counter is containing the address of this instruction. So program counter contains the address of instruction. In fact, next instruction. to be executed. And so with this thing in mind, the important takeaway is that this number 100 is stored as the hexadecimal digit over here, and that is stored as part of the instruction. That is known, so this 0064 is actually the number 100, right? So that is an example of an immediate addressing mode when the data is stored as part of the instruction. Next is the index addressing. So in this case, the address of data in the memory is in a register. So again, our goal is to access memory. The instruction is LDR, load register. LDR stands for load register. So load register, which register needs to be loaded? This is the register R0. In this example, that needs to be loaded with what? With the contents of the memory pointed to by register R1. So R1 register contains the address of memory. It contains an address of the memory. So for example, if R1 contains hex 2000004, then we are really talking about this part of the memory. And in this case, this is the division of memory, that is the RAM. So here we have some data 1, 2, 3, 4, 5, 6, 7, 8. Again, it's a 32-bit number. And this number is going to go into register R0. So the contents of R0 after the execution of this instruction would be 1, 2, 3, 4, 5, 6, 7, 8. This is an example of index addressing, where the memory address is stored, or the memory is indexed by the value of the register. So this R1 written inside the square bracket, this R1 contents will be treated as address. And we are going to go to that memory address, that is 20000004, and fetch the data and put it in the destination register R0. This is what index addressing mode does. The third addressing mode is known as the PC relative addressing. In this mode, we are going to first look at the syntax of the instruction, and we have been using that instruction from the very beginning. So example, load register R1, comma, equals to count. So what do we mean by this part that is equals to count? What do we mean by that? Let's try to understand that. So equals to count means essentially that we are talking about the address of variable count. So equals to count means the address of the count. Okay, where is that address stored? Where is that number? So again, the address data, they are all numbers. It just depends how we interpret those numbers. So the address is stored in the ROM section of the memory. That's where the code is stored. So this equals to count is actually an address. It is stored in the ROM. It is stored in the ROM. So in this example, let's say the address is hex 2000040. Okay, now what I'm going to do is that I'm going to store this address in the register R1. So R1 contents are now equal to hex 20000000. And then we are going to apply the index addressing. So the second instruction is LDR R0 R1. Therefore, we are not going to, so remember, as we saw in the previous slide, the index addressing, whatever, when our register is written inside the square bracket, so we are going to treat its contents as an address of the memory. RAM to be specific. So we are going to say that R1 contents are actually address of some RAM location. So say that that is an address, so go to that address. So we are going to go to that address. Okay, so that address is here, and that's where the count variable is placed, and we're going to put those contents, whatever 32-bit number is here, we're going to put that into R0. So this is actually, in fact, the first part is a method of accessing memory, again indirectly, by first storing its address, and the address is stored in the ROM. Whenever that happens, the address is stored in the ROM. Whenever that happens, and we are going to access some portion of the RAM based upon that address, that is known as the PC relative addressing. So continuing with our discussion on the memory access instructions, we saw in the previous slide that the PC relative addressing mode had a syntax that LDR register comma equals to some variable. So that can be a variable, or it can be, and that variable stored somewhere in the memory, that is the RAM, or it can also be a label of an instruction. So this number actually points to some data, and this label might be representing some instruction. It can be used for both purposes. So data or instruction, both can be accessed using the PC relative addressing mode. Sometimes we need to add to the register containing the address that further needs to be referenced. That's where we need some base address contained in the register, let's say R0, and then we add some offset to it. So we add some offset. In this case, the offset is number 16. So that syntax is R0, comma, hash 16. We don't put a plus, rather we say R0 hash 16. That's base plus offset. And remember, we can also use store instruction as we saw in the previous slide. So we can store, so these load and store are the only ways that we can access memory. Load means load data from the memory or some address location in the memory, and the store means store data to that location of the memory. There is a lot of flexibility provided by the load and the store instruction format. So in the first thing to note is that there's a type suffix that allows us to give more meaning to the load and the store instruction, because we might be accessing not just 32-bit, we might be accessing data in 8-bit, 16-bit, or 32 bits data. So that flexibility is there in the load and the store instruction. So if the type, so there are different options of type. If the type is B, it means that we're going to load and store unsigned 8 bits, unsigned. And if the type is SB, means that we're going to load and store signed, 8-bit signed 8 bits. H means unsigned 16-bit Harford. So here we're talking about 16 bits. And SH means signed 16-bit Harford. So and then if there is D, then we're talking about fetching or storing 64-bit number, which is actually very rare, and we're probably not going to use that in our class. However, if there is a case that we wish to fetch 64 bits of data, then we need 2 registers. And if there is no type, then we're talking about just 32-bit load and store instruction. And among the listed instruction, some of them, the format of some of them have been already described, but I think it would be worth explaining the last two instruction where we have for quite a few registers. So here we say that load register RD based upon what? Well, Rn, Rm, and then logical shift n. So we are first going to perform a logical shift operation, or Rm, and the shift amount is n, and store the result in Rn. Oh no, actually this is we're going to, sorry, let's do that again. So we're going to perform logical shift on register Rm and then add it to Rn. So essentially this is what we are doing. So logical shift applied to Rm, then Rn. So the sum of the two numbers will be referenced as an address, and we're going to go to that memory address, fetch data, and put it in RD, right? So the actual address is Rn plus shifted version of Rm. That is the address. So the address calculation is important. And the final one is again the same. We're going to calculate the address by shifting Rm and then adding it to Rn, and then that store data stored in RD to that memory address. And now it's time to talk about a stack. I'm assuming that the students have some familiarity with the stack data structures that is based on the last in first out storage mechanism. And in this, utilizing stack poses a foundational restriction, that is that we're only going to push or pop, push and pop will be described later in the lecture, but we are only going to store and retrieve data in 32 bits when we are going to use stack. The important register to consider over here is R13. So SP register R13 is again a special purpose register, and this is going to point to the top element of the stack. So the stack pointer will start somewhere at the top of the stack, and it will be decremented. So the conception is that if this is the stack area that you wish to use in the program, then the stack pointer will start over here, the topmost address, and then with each time you put data onto the stack, it comes down like this. So that's like the push operation, and the pop operation goes in the other direction. So when you pop something, the stack pointer is incremented. That is so this is the SP, we say incremented, and over here when we perform push, SP is decremented, it goes down. More on this will come in the next slide. So the two instructions that help us utilize the stack portion of the memory are the push and the pop instructions. So the push instruction is going to push data onto the stack. So for example, if we assume that the memory is memory addresses are decreasing in this direction, so you know so this is the address space defining the portion of the memory containing stack. So each time you push, so in the beginning, the stack pointer is pointing at the top address of the stack, which is hex 20007FFC. And if you push, then the stack pointer is actually decremented, although on the diagram it is shown as if the stack pointer is going up, but actually the addresses, it is actually moving, the stack pointer is actually moving towards lower addresses. So it is moving towards the lower addresses, and each time you push, the stack pointer moves to the lower address. And conversely, if you perform a pop operation, the stack pointer, suppose it is over here, then each time you pop and the syntax is that you pop and retrieve the data pointed to by the stack pointer and put it into some register R3. The same goes for the push instruction. The argument is inside the parentheses, and within the parentheses we have some register. That means, of going back a few steps, we said that when push R0 was performed, meaning that whatever the contents of R0 were there, those were pushed onto the stack. So here R0 was stored, here R1 was stored, and here R2 was stored. Okay, so when you pop, you increment the stack pointer by 4 because each time you push or pop something, it is always going to be an increment or decrement of a 32-bit number. 32-bit, so it is always going to be a data in 32-bit size. So pop will increase the value of SP. So in this case, whatever is stored over here is put into R3. Over here, whatever is stored where the stack pointer is pointing is going to go into R4, and whatever is stored over here is going to go into register R5. So this is how the stack works, and one of the important uses of the stack is the storage of some temporary data that we wish to store and retrieve in a specific order, and those are often utilized in the implementation of the routines and subroutines. But before that, there are some rules to use stack. Stack should always be balanced. That is, whatever function that we wish to implement should have equal number of pushes and pops. Stack accesses should not be performed in the area that is outside the allocated area. So remember, this is so the portion of the memory that is allocated to be used as a stack runs from hex 2000040 all the way to 20007FFC. So within that area, you're allowed to move the stack pointers, and the stack pointer should not be placed outside the stack area, otherwise the program may become unstable and may not work properly. So that's the rules that we need to keep in mind at all times while using stack. Stacks are specifically useful for the implementation or the execution of routines and subroutines. Alright, so in this case we have a main program which initializes some number equals to 0, and then it invokes a routine. So this is the routine that I was talking about. The routine in this example is a change. So that routine called change is going to change the number. And how does it do that? Well, in this routine we are going to add 25 to the number, and then we return. So this main program is going to call this routine change, or to call this function change, and then it goes back and then call that function again, and it keeps on calling the function. That's it. So how to do that in the assembly language? Well, we're going to define the assembly code for the routine first. So where is that code for the routine? So let me draw the border within which the routine has been implemented, right? So this is this change routine implement. This is how the change routine is implemented. Okay, we'll come back to that later. What about the main part of the program? The main part, this guy, it is implemented over here. Now first look at the main portion. We're going to store a number. So first of all, this is the first instruction of the main. There's a label over here, main, load register R1 with the help of the PC relative addressing mode equals to num. So this is a number. This is actually a constant stored somewhere in the memory, we're going to and that constant number is going to is actually an address where the actual content of the variable num is stored. So that goes into R1. And then we're going to move R0 to 0, and then we're going to store. So we are essentially the first three commands have done what it has. So if this is where the number is stored in the memory, let's say the RAM. So the first three commands have put 0 in some memory location in the RAM. That memory location contain number NUM, and then it says BL change. BL means branch and link. Essentially, it says that once you have executed these three instructions, it is now time to jump and to execute a routine called change. That is, we are jumping over here. So we jump to the change. But before we do so, we are going to store the return address on top of the stack. So we're going to store the address. So what is the address of this instruction? Okay, that instruction. Which instruction? This one. So it means that after executing this change instruction, the change routine, we are going to come back over here. So it must have some address, and that address is going to be stored on the stack. So we are going to store the return address. So this is the branch and link stores return address on the stack. And what is the return address? The address of the next instruction to be executed once the function has finished executing. Okay, so on top of the stack we now have this return address. Okay, so now we go and execute the routine. We load the number value into register R1, the address into register R1, and then obtain the value of that number, add 25 to the number, store it back to the memory. So now the memory will be updated. It is now going to be 25. So number equals to 25 after the execution, the first execution of this function or routine called change. And then this instruction bxlr, this is what I explained before. bxlr, it is like a return. Okay, return what? Return. So essentially this instruction pops the return address. It does what? It pops the return address from top of the stacks and put it in the PC, so that PC now contains the address, and this address is basically the address of this instruction. So now we know that the program counter, which tracks the address of the next instruction to be executed, has now the value that is pointing to the address of this instruction. I know it is getting a bit too cluttered. So remember, address is the address of this instruction. Let me erase this real quick. So address of this instruction over here. So this is the address of the instruction. And PC, the program counter, now contains the address, means that we are going to resume execution over here. So after executing this routine change, we have successfully returned to resume our program. And the next instruction is B, branch loop. So B means just branch. Okay, branch where? So branch is like jump. You can say that you are instructing the program counter. So jump PC where? where do you want your program counter to jump? You want to jump it to the instruction whose label is loop. This guy over here, instruction whose label is loop. So PC is now coming over here. It is now pointing to the loop. And again, when you execute this loop, the instruction whose label is loop, we say that go and execute the subroutine change, and we come over here. And before executing the routine, we're going to store the return address on top of the stack, and we do that whole procedure over again. So this continues, and the program implements the simple program, simple addition task, in which each time you execute a routine, it adds 25 to the number. So next time it will be 50, and after that it will be 75, then it will become 100, and so on. Here is another example of how you can use the stack indirectly to call a subroutine that is inside another subroutine. So if, for example, we have a subroutine known as the divide, and it uses some arithmetic instruction that we haven't discussed, but we don't really care at this point. Basically, it is just dividing two numbers. The main task over here is to generate a random number between 1 and 100, and then that random number is generated by means of some arithmetic. Let's look what is that. So the first thing is that we want to store the return address. We're going to push the return address onto the stack, and that's because within this routine rand 100, we are going to call another routine that is branch ending divide. So this is a routine, so you can call this divide as subroutine, and you can call this ran as just routine. And there is another, like a main, the main part of the program that calls routine, and the routine calls subroutine. But then we have to figure out a way, once the subroutine is executed, we want to go back to the routine and then find a way back to the main. This is the idea. So if we know, or if we're sure that we are going to call a subroutine, we're first going to store the return address, and then perform some arithmetic and come over here, BL divide. Okay, BL divide. So this branch and link divide, because this is the call to the subroutine, and after executing subroutine, we come back over here and retrieve our main return address that will eventually take us back to the main. So essentially this instruction is required so that we can find a way back from routine to the main. So branch and link LR should be the last instruction of the routine. That essentially does what it pops the value of the return address and put it back into the program counter. So far we have seen that one can program microcontroller using assembly language. In doing so, however, even a simplest of tasks requires several lines of code that may be difficult to write, debug, analyze. So it is somewhat less user-friendly. In the form of C language, however, there is a viable alternative. That's because C is a high-level language. What do we mean by that? Well, it is a bit more abstract. It is expressive, readable, and analyzable. And it requires a fewer lines of code to implement the program that we wish to execute on a microcontroller using assembly language. So a concise program is one advantage. Besides, C is a procedural language. It executes instructions step by step in a sequential manner. And the program can be composed of several procedures, functions, and subroutines, as we describe in the case of assembly language. but they are a lot more concise and readable and analyzable. And C code is compiled after being analyzed as a whole, not just line by line. One of the nice things about C is that it is very popular, and it is not too far away from the machine. We saw that when you're writing a code in assembly language, you are programming the microcontroller in a way that you feel very close. The instructions are written in a way that the underlying hardware functionality is fairly transparent. That's what we mean by close to the machine. So C is not that far, I should say, it's not that far from the machine. It is still close to the machine, so it is close to the hardware, and straightforward, and it has influenced several other languages, high-level languages. And the nice thing about C, another nice thing about C is that you can, because it is not too far from the hardware, you can write drivers, runtime system, operating system, and schedulers. So there is always a trade-off that you find among programming languages that are used to program the microcontroller. If you have, if you want to have higher abstraction, then you have to migrate away from the hardware. So abstraction means you are moving away from the hardware. So lower abstraction means you're closer to the hardware. So high abstraction, hardware friendly. So low abstraction. But in case of assembly language, the abstraction is too low, and then that's where the code becomes difficult to analyze and write. So this C sits somewhere over here, I should say. It is still close to the hardware, and it is a very good choice for programmers to write their code in a concise manner that can be later used or reused or to modify and to implement a different application. Some merits of using C language is that it comes with a lot of built-in functions. A good example is that of a printf, which is used for printing purposes, and those and similar definitions are included in the header files that we introduce as a preprocessor directives include. So some built-in functions can be used when we are programming using C language, and it has a main function that resets the PC, the program counter register, telling where to start from as far as the execution of program is concerned. So there's a reset vector at ROM location at 4. That's the starting point that initializes the program counter. And it initializes the global variables, some of those that we have discussed in our lecture today. And then the development process is such that there's a C compiler that translates your C code into the assembly code. So you can actually see what assembly code is going to be implemented or going to be executed and will be responsible for running your program on the microcontroller. And then the assembly code, maybe I should have said that in the very beginning, but assembly code is converted into the object code. That is the actual code. It's like a machine code, or something very similar to the machine code that runs on the machine. So there is still a layer of abstraction between the assembly code and the machine and the actual machine, and that's the object code. So from C we convert the program from C into the assembly language, and then from the assembly to the object code that runs on the machine. So C program structure, we're going to use functions and subroutines. We're going to use variables, types. There are going to be instructions in the form of statements. So remember, these statements are actually the instructions. They're going to be translated. If you translate the C language statements, they are going to be translated into the instructions of assembly language. So these two are equivalent in terms of their function, and then there are preprocessor directives that we talked about, like the one that we see before, include something like IO, stuff like that. So those will be covered in detail in the next lecture. We're going to utilize the structured programming version of the C, not the object-oriented version that much. So functions, variables, statements, expression, names, operators, comments, and syntax. So in structured programming, we're going to follow the sequence, one statement after another, written and executed in a sequence. The sequence can be split into subsequences based upon specific conditions. So those conditional statements are going to disrupt the sequence, and we have to choose one of the two paths or multiple paths. And then there are some loops, like the for loop and the while loop, that we can use to perform the iteration within the program. Right, so with that, I would like to conclude our second lecture. I hope you enjoyed listening to this lecture, and you may have lots of questions. For that, we are going to have our regular Q&A session. This week, however, I think the time has changed. It is going to be 11 a.m. So till that time, stay safe, and bye-bye. And before that, I should give slight credits to Jonathan Volvano. These slides are taken from his permission, and these have been modified to fit to our needs with appropriate narration.